So yeah, we will just improvise. So as far as the three algorithm strategies go, uh, Gail talks about something called BUD. And BUD, this is the acronym. It stands for bottlenecks, unnecessary work, and duplicated work. So she gives an example of, there are two arrays and you have to find out if one element exists in the other array. You have a couple of choices here, right? The brute force is you iterate over the elements of the first array, and for each element you're going to look for that element in the second array. And so when you have this kind of, a nested loop, your time complexity actually becomes O(n) squared, or O times B, where A is the number of elements in the first array and B is the number of elements in the second array. And then, so she talks about how can you reduce this time complexity? And ideally, we'd like to get to a time complexity of O(n) versus O(n) squared. So one of the ways, and this is a quick way to kind of improvise on your solution, is to look and see if you can use hash maps. And so in her example, she has the second array, and I'm going to actually improvise right here. So like we had the first array, which was like say you have 1, 2, 3, okay, 4, 5. And then you have B is equal to maybe 4, 5, 6, 7. So then she breaks it down. She says, what if you were to convert, maybe we could optimize and choose maybe the longer the longer array. But for now, I'm not going to optimize. What if I took B, which is a list, and I converted B into a hash map? And so when we convert B into a hash map, then in order to see if each of the if elements in A exists in B, we don't have to do a comparison with each one, because you just look you just check and see if this key is in the hash map. And so that is an O(1) operation. And so basically the time complexity here becomes, well, there is going to be, OR of B here, because you have to convert this into a hash map. But in the second step, you're just looking for A in B. And in that case, it's just going to be, you're going to add, it's going to be a time complexity of OA. So effectively, you have a time complexity of OA plus B. So this was basically her example that she gave. So that's something to just think about. And let me go back here. So the next one she talks about is unnecessary work and duplicated work. So unnecessary work, again, here is, here, if you go back to our example, the unnecessary work here would have been what? Like the part where we are always going and checking for this element in this list multiple times, right? You're iterating through this. So that's your unnecessary work and duplicated work. So these just different techniques to kind of optimize your solution. Also, she talks about something called DIY, which is use a really big example. And the example that she gives is, look for permutations of S in B. This is, so let's say S is equal to A, B, C, D. And you have another string B, which is equal to B, A, D, C, then C, D, A, B, and so on and so forth. So you could also have D, D, A, B, and so on. So how are you going to look for permutations of this string in this one? How would you actually go about doing it? So she says that what you should actually do is come up with some really big examples. So for example, here, I could take this and I could just play with this, okay? Because permutations, by permutations, I mean, you can have different combinations of these letters, right? So when you see these examples, then your mind is automatically going to start thinking, okay, how would I go about doing this? I'm looking for permutations of S and B. Well, I do need four, at least a minimum of these four characters. Okay, so I would start perhaps going this way, and then maybe I could actually slide down, right? And just go sliding down and see if these characters they exist in this. And for those of you who attended the previous mock interview, we talked about anagrams, right? So what are anagrams? So anagrams is where you can form the same word, right? Using because you, let's say you have two words and they have the exact same letters, maybe they are kind of all mixed up, but you can so S is an anagram of S1. If S1 is maybe DCBA, right? It has to be the same length and it has to have the same characters. So as you're going through this, you might just start coming up with some ideas and that could help you with your brute force. So that's why she talks about using a really big example. So just to summarize, so we have Bud, and Bud is the bottlenecks, unnecessary work, and duplicated work. And then do it yourself. Use a really big example. So today, what we are going to work on two problems. The first one is the middle of the linked list, and the second one is word subsets. And for this part, uh, I'm going to bring up a whiteboard because we like to simulate an interview environment. So I'm going to bring up this mock interview. And I'm going to invite Elaine to join. And hi, Elaine, how are you?
Hi, I am.
Hi. All right, Elaine. Today we're going to work on, I have a problem for you. And the problem is we have a linked list and you have to find the middle element of the linked list. I'm going to just share with you briefly what the problem is. So you're given a non-empty singly linked list with head node head. You have to return the middle node of the linked list. Now here are the constraints. If there are two middle nodes, return the second middle node. So here are our examples. So you have input 1, 2, 3, 4, 5. And so here we have an odd number of elements. So here the middle node is 3. So the output should be node number. So the return value has to be 3. All right.
Sounds good.
And then we have a second example where here we have an even number of elements. So the two middle, actually in this case, it would be nodes because we're working with the linked list. But so here you have 3 and 4. These two are the middle nodes. And so the constraint is that if there are two middle nodes, you have to return the second middle node. So in this case, we would actually return 4 because 4 is the second middle node. Okay. Now, before Elaine starts talking about her brute force algorithm, I would like to invite our participants to just take a moment and come up with some ideas. How would you approach this problem? So note that you're working with a linked list and you have to find the middle elements. And you have to bear in mind that there could be an odd number of nodes or an even number of nodes. So I invite you to actively participate, but you don't, you can maybe post your comments or share your thoughts on the chat so that we are all engaged. So with that, I'm going to turn this over to you, Elaine. You can go ahead and share your thoughts and ideas as to how you would approach this problem.
Yes, thanks, Daniela. That was a wonderful explanation. So I see a couple of approaches in the chat, or maybe just one approach. So the first approach that I will take is maybe more of a brute force approach, and it makes use of our hash map topic that we've been covering recently. And that approach is to turn the list into an array. So if we have a list like this, we just traverse every single element. So starting from the head node, and we copy that node into an array. So starting from the head, while we have elements, we would start and look at the first element, append it to the array, then the next element, append it to the array, and keep getting next nodes until we reach a none node. And then at that point, we will have the array populated with all the nodes in the list, and then we can simply take the length, I'll call our array A, and take the middle index. And here you want to be careful about your odd versus even. It turns out that if you take the floor of a division by 2, you will get the middle element of an odd array, odd length array, and you will get the second of the middle elements in an even array, even length array. So that's the first approach. And Daniella, would you like me to code that out?
Well, can you share the time complexity for this approach?
Sure. So we'll say the steps are like here, 1, traverse, linked list, add each node to array, stop when you reach the end. Well, we add each node exactly once per node, so then our time complexity is order n.
Okay.
Yeah.
Mm-hmm. Okay. And what about the space complexity?
So the space complexity is the overhead of keeping this array, which I should mention is basically, an array is like your most basic hash table where the keys are indices.
Right.
So the space overhead of that array is n nodes. So also order n.
Okay. All right. Very good. Now, can you share a solution, or can you think of a solution where we can eliminate this space complexity of ON? Could we do it without having to allocate? Could you solve this problem without having to allocate additional space?
Yes, I will take my help from the peanut gallery.
Okay.
A lot of people are talking about the 2-pointer technique.
Okay.
So
Awesome.
2-pointer technique. So the idea is that thinking about our algorithm strategies, you might realize that there's a bottleneck here, where in this first approach, we had to touch every single element of the linked list. And the key with the 2-pointer technique is to realize that you don't have to look at every element because you just need the middle element. So you just need some way of knowing where the middle element is. And one technique to do that is to have a slow pointer that advances by 1 and a fast pointer that advances by 2. And if you move them in tandem, when the fast pointer reaches the end of the list, slow pointer will be pointing to the middle element. So that's like not even pseudocode, just a description of the approach.
Very good. So what would be the time complexity in this case with the approach 2?
Right. So just copying down our linked list here to illustrate. Let's say we start both the slow and fast pointers at head, and then I'll only do this a few times. In the first iteration, you would advance, so they're both starting at node 0, let's say. In the first iteration, slow goes to element at position 1, fast goes to 3, and then the second iteration, slow moves to 2, and fast will move to 4. And we can see that at that point, hopefully your end condition, termination condition, will say, okay, fast has reached the end of the list. Slow is pointing to the middle. We've looked at 0, 1, 2 elements, or sorry, we've looked at 1, 2, 3 elements in a 5-element list. And in general, we're going to stop at the midpoint. So in general, we're looking at half the elements, half of n. But because we're looking at big O, we drop that constant, that multiplier in the front.
Mm-hmm.
And so we're looking at O of n time complexity. So the same, roughly speaking, as our first approach.
Okay, very good. I think in step 2, so slow pointer moved to 1, and I guess the fast pointer would have moved to 2, right? 0 plus 2. That's just a small thing to observe. And then, yes, and then fast pointer goes to 4, and as the slow pointer gets to 2, and voila, we have a middle, because after this, the fast pointer doesn't have, the fast pointer next will be none. Okay, that looks pretty good. Can you code the solution for us?
Yes. So this will be rough. I'll just use Python.
Okay.
So we'll initialize our slow and our fast to be pointing to the head of the list. And
so may I ask that that you just code like with a def? Okay, awesome. Instead of the pseudocode. Middle node, awesome.
List. So let's say that we're given the head of a list, and I'll just rename it that. So then we're initializing our 2 pointers, slow and fast, to point to head. Sorry about the capitalization.
That's okay.
And then, so I'm just going to put a little asterisk on the while, because I know that in my example, the end was that the fast.next is none. And I will come back to deal with the even number case. So in Python, that evaluates to true if it's a node. So I'll just keep going. While fast.next, we advance our slow by 1. Slow equals slow.next. And then we advance our fast by 2. Fast equals fast.next. Next.
Okay.
And then we return slow. So in order, this has a bug. And to find that bug, I'm just going to look at the even number case first. So we have 4 elements here. So we will start them both at both pointers at element 0, slow, fast. And then basically you want to keep going. So we advance it by 1, fast points to 2. And then one more time, 2. And now fast points to, so fast.next, so 2.next would be 3. 2.next.next would be none. So in the even number case, we want to terminate when fast is none. And we can capture that by saying while fast and fast.next. So kind of explaining this out of order, but if we check in the even number case, the fast pointer will end up on the none node because it's always skipping to the next whole number of pairs. And so we want to terminate if fast is none in the even number case. In the odd number case, which is what I started with, fast will end up on the, you can think of it as the unpaired last element, in which case you want to check that its next element is none. So that covers both the odd and even number cases. And then we want to check that we can just simply return slow at the end. So so here is where our even number case starts. And then here was our odd number case. So in our odd number case, slow was indeed the middle element here at index 2. And in our even number case, slow ended up in the higher of the middle elements, which is what we wanted to return. So I have demonstrated that for the slow example, or the small examples.
Yes. And I like this additional check because this also protects you in the case where head was not in the first place, right? So let's for the case where you have a link, an empty linked list. So head was actually none. So then this actually is a good check for that as well. Okay.
Right, so there was something in the chat, if the linked list has 1 or 2 elements, then we need to handle that separately. Well, I think you just...
That is a good question, actually. Let's look at what they have here. So first of all, this is a non-empty singly linked list.
Right, yeah.
And so I guess the case that they're bringing up is, these are some edge cases, right? So what if you just had a single node, and the second case is where you have 2 nodes, right? LeetCode has not given specific rules as to what to do in this case. But if you go by what they are saying is when you have an odd number, this is interesting. How would your code behave in this situation? Let's see.
Sure, so I'll take this one first. So then we've got slow and fast will both be pointing to that first node. And then this is right, its next is none. So then fast.next is none, which in Python is false. So then we would just return slow, which might not be what we want. What is the middle of a one element list? I don't know, but we would return S, which and S equals the node one. So that's the one element case. In a two element case, and let me put in none here, just so we all remember. Again, slow and fast are pointing to one. And the next iteration, slow goes to two, and fast is pointing to none. And then because fast is none, the while loop is false. And we would return slow, which is the second element in a two element list, which again, it would be up to the interviewer, the problem writer, if that is a valid output or not. But you wouldn't error, so that's maybe good, maybe not.
Yes.
Return S equals to 2.
Yes. Yes. So this is a good example of a clarifying question to ask at the start, or I know and this was brought up by somebody on the chat. So that's awesome that was brought up, because these are additional test cases, right? Where you just have a single element or you just have two elements, and be interesting to just know from the interviewer, that would be me, as to what is the expected behavior. So I'm going to say that if we just have one element, this is fine, that we will just return the single, the one element. And if we have two elements, we're going to return the second element. We'll provide clarification like that. All right. Well, great job, Elaine. I like the way you shared your brute force solution. You shared the time complexity, space complexity, and then you improvised on the space complexity. You also worked through the different cases, like specifically when you have an odd number versus an even number of elements. You also were able to identify a possible bug, and refine your solution. And then also thanks to those who posted the additional test cases on the chat. So that was great. So with that, I'd like for us to, I'm going to actually stop my share, and we're going to jump to the chat. And let's see. So I know Michelle, you're probably recording the session right now. So could we pause this recording? So, okay.
And we're back. We're back to another mock interview with Women Who Code San Francisco. So here I will be playing the interviewer, and we have our longtime mentor, Daniella, who will be the candidate. And her problem today is called word subsets. It's LeetCode number 916. I'll just go over the problem. So you're given two arrays, big A and big B, of words. A word is a string of lowercase letters. We define the word little b as a subset of another word, little a, if every letter in B occurs in A, including multiplicity. So the first example here is the word WRR, and we are showing that it is a subset of the word warrior. And that's because every letter in WRR occurs in warrior. Namely, there is one W in warrior, and there are two R's in warrior. But WRR is not a subset of the word world. There is one W in world, but there is not two R's in world. We define a word little a from the set big A as universal if for every word little b in the set big B, the word little b is a subset of A. And Daniella, your task is to return a list of all universal words in A. And I'll go ahead and go through a couple of examples here. So the first example, our set A are these words: Amazon, Apple, Facebook, Google, LeetCode. Our set B are these one-letter words, E and O. And so universal words are that for every word that's in B, though each word is a subset of a universal word that is in A. So when we look at Amazon, E is not a subset of Amazon. So Amazon is not universal. When we look at Apple, E is a subset of Apple, but O is not a subset of Apple. Therefore, Apple is not universal. Then we'll look at Facebook. E is a subset of Facebook and O is a subset of Facebook. So we add Facebook to our output. And the same for Google and LeetCode. Both of those have one E and one O. And so Facebook, Google, and LeetCode are our outputs for that example. And I'll just go through one more example here. And that is this example 4. The output is Google and LeetCode. And we can see that both of those have L, O each once. L, O is in LeetCode. And they also have E, O, and in Google, and E, O in LeetCode. And one thing to notice is that even though there is an O in one word of B and an O in another word of B, LeetCode only has one O.
Okay.
Some constraints here on length, relative length. You only have lowercase letters, and all of the words in A are unique. And I am just now noticing that the same constraint doesn't hold for B.
Okay. All right. All right. Well, thank you for sharing the details of the problem and the examples. I wanted to just go over a few additional examples, and I'm going to just modify the examples. That's okay. Let's see. What if B, the list B, consists of okay, and so the list of words in B, they could contain these letters that can be repeated. They can appear multiple times, right?
That's
like
right.
in this case, okay, got it. So like if you had APP, then this is a subset, LE. So this would just come down to Apple, because we don't find, this is not a subset of these other words. Okay.
Yep, that's right.
Is it possible for the A list to be empty, or can we assume that it's always going to be non-empty?
It is non-empty.
It is non-empty.
It's,
it is greater than or equal to 1. So it's going to be non-empty. But the maximum number of elements in each of these could be up to 10,000. Okay. Yep. And the length of each of these elements could be they could be 10 characters long. Okay. Okay. So I have just a brute forced solution where I would iterate over each of these strings in A, and then for each string, I would check to see if each of the elements in B is a subset of the string in A. But that would require me to iterate over A, and then for each A, iterate over B. And that would really bring my time complexity to O, A times B. But it could be even worse than that, because for each element in B, I'm going to be looking to see if each character is present in these words. So I feel like this is not a very optimal solution. And I want to see if there is a way we could improve on the time complexity here. So let me look at this again here. So B consists of these strings A, P, P, L, E, and A. And what was required was we needed to, for as far as the letter A goes, there needed to be a word that has at least, it had to have at least one A, it had to have two P's, one L, one E. Same here, if when I look at these Facebook and LeetCode, I have one E, one C. So it's a single E, a single C, and a single O. And here, again, we need one L, one E, and one O.
Yeah, I agree with all that.
Mhm. So what if we could do some kind of pre-computation to eliminate this extra work? Because right now we are doing some extra work for we take every A, and then for every A we are going through B, and we're looking for these letters in A. What if we could do some pre-computation where we kind of process these elements in B, and we would use a hash map to keep track of the count of the characters that are required. And it's not just like the sum of all the characters, because basically it's not like we need two A's. We need so for example here, or rather this is a good example here. uh, we need one E and we need two O's. And here, if mm, so going by this example for the APPLE, we could say we need the number of A's that we need is a maximum of just one. The P's we need is basically the maximum number of times a character appears in a word. So, for example, if we had A, P here, right? Well, the character P is only appearing once here, but P appears twice here. So we need P at least a minimum of 2 times. So if I could keep a track of the count of the characters and the uh, maximum, okay, actually, I'm going to just keep, if I could keep track of the maximum count of each character that is required, if I could do this pre-computation and have it at hand, then all that would amount to is I would just have to iterate over this, and I could basically use a hash map for this, and then I could actually um, look for these characters in this particular hash map. Also, to optimize this, I could also convert each of these strings into into a dictionary by using the built-in Python class count. And so what that would effectively do is it would help me bring down the time complexity from OB to OA plus B. So we're actually going to be doing 2 steps. One is just the pre-computation where we just work with B. And I have a hash map or like a counter for each of these, basically a counter that just keeps track of the maximum number of each character that is required. And then the step 2 is we then iterate over B, looking for the universal string. So that would be the time complexity.
That sounds good, Danielle.
All right.
How about while we're here, the space complexity?
So for the space complexity, if we are going to be using these counters, the space complexity for actually B, it would be the so these are all lowercase letters. So depending on how many lowercase letters there are, okay, so then that would be it would be the count of lowercase letters. I think there are 26, if I'm not mistaken. But it would depend on that, the count of the lowercase letters, because we're just keeping track of that. Let's assume that there's a word that has all the lowercase letters. But we also know that that each of these strings can have a maximum length of 10. But you could have a mix of letters. So I would say that it would be like O of it's actually a constant number. So
right, yeah, I agree.
Yeah, that would just be constant. It's not varying. It would actually, I think that would actually translate to O of 1. I know if it's O of a constant. That is the number of lowercase letters. So I'm just going to put that for the space complexity. That would be for B. Now, as far as A goes, for A, we are going to go, we're going to create, again, we're going to be using counters here. And for each element in A, we will create a counter, because we want to look at each of these letters, right? So in the case of Amazon, I know that I need 2 of A's, 1 of M, 1 of Z, 1 of O, 1 of N. So then that would be depending on that would depend on my length of my string. So if I have 10, right, then it's O of 10, but then it's also multiplied by um, the the length of A. But the way I plan to implement it is we won't be allocating all that space upfront. It's going to be in a loop. So for now, I would say again for the space complexity, it would again be O of length of the string, so O of 10. So again, O of a constant. So I think space, we are pretty good. It would again be, so let me put here time. This is the time, and this would be space. So space would be O of, I'm going to put O of 1 because it will still be constant. Now I might revise this. Let me just think through this again. As we look at, I would be iterating over this, and for each string I'd convert it into a counter. But and each string has a maximum of 10 characters. So okay, I think I'm going to stick to O of a constant. So that's space. Does that sound okay?
Yep, sounds good.
All right.
Some code.
Okay, sure. Awesome. Okay, so we'll get coding. So I think it is word. Okay. So we're going to call our method. It's going to be word subsets, and we are given two lists of strings. So we have A, which is a list of strings, and we are given B, which is also a list of strings. And what we have to return is a list of strings A. And these are all the universal strings in A. Okay, so the first step we want to do is we want to get the required character counts. So given B, we want to know, so this would actually be a counter. So required character counts. And so the counter is one of these built-in classes in Python. So for hello, counter of hello would give you h of 1. It's actually derived from a dictionary. So key is E value 1, L value 2, and then O would have a value 1. So this required character counts is actually a counter like that. It would tell me, okay, we need this. This is the count of this specific character that I actually need. So we're gonna, so I'm just gonna put this down here. So get required character counts given B. I'm just gonna pass it for now. So once I have the required character counts given B, what I want to do is so this was my pre-compute step. I want to now find these universal strings in A. And basically for this function, I would basically pass my required character counts. And this will actually return the results to me. Okay, so when we came to space complexity, here we would have to allocate additional space for our result. So we got to take that into account for our results. So I'm going to put an asterisk here because I have to revisit this. Okay, and basically this is what I would actually return. So this is the way I would actually break this down. So then find universal strings in A and whatever this required counts. And let me fix any typos here. My results is initially just equal to this. Then I would return my results. All right, so I'm gonna move this over. Okay, so here we go. So I also want to copy an example. So we'll copy, I'm gonna take this example, maybe choose a bigger example for now. Okay, so here, let me have this out here. Okay, so the first part we're going to code is get required character counts for B. So given B. So here we know that B is a list of strings. Okay, so the first thing I'm going to do is I'm going to be using the counter class. So I'm going to declare, so I have required character counts. This is like an instance of the counter class. I'm just going to initialize it with this is just an empty string. So it's not going to have any elements in it right now. And then what I do is I'm going to iterate over the elements, these strings in B. So for B in B, okay, I'm going to convert, like for example, EC, I'm going to convert it into a counter. So B counter is equal to, I'm going to take counter and I'm going to pass in this particular string B. So for example, EC would get transformed into E1, C1, a dictionary. So you have B counter. Now, over here we have for each, now I have to go for each letter in this B counter. So basically, I'm traversing that particular, like the dictionary with the keys, each of these characters. For each letter in B counter, this required character counts at this particular letter. So I have to store the maximum number, right, of the count of this letter character that I actually need. So it's going to be, I'm going to use max, and I'm going to do required character counts for this particular letter and B counter for this particular letter. So that's what's happening. And then at the end of it, we just return required character counts. So for example, if I had B, let's see how this works. If I had B of C, I'm just going to choose an example, C, E, E, O, or I had something like O, O, C. So initially this counter will be this is empty. I'm going to go through each of these strings. I've converted this into a counter. And for each letter in this B counter, so now required character counts will be such that for this first parse, E is going to be, so that would be 0, and B counter of letter, that's going to be 1. So, and we'll have C will be of 1. On the next iteration, again, I'm going to convert this into a counter. And here, O is going to have 2. Well, C is 1, and this 2 is 1. So C stays as 1. And the next one for C, E, E, O, C stays the same. But now E, I need at least 2 of E's. So 2 comes here well, O is going to stay at 2 because this is just 1. So that way, this basically, this pre-computation steps kind of it tells me that I need 2 E's, 1 C, and 2 O's. So let's confirm that. At least 2 E's, 1 C, and 2 O's. So that's what this is going to give me. So this is the first step here. All right.
Yeah, and just a quick check. Yeah, your algorithm is sound. And maybe just as a Python question, does counter throw a key error if it's initialized with an empty string? If, you know, on the first time that you touch the required char counts, that letter is not present?
That is a good question.
Well, as the interviewer,
The required character counts, I think it just gives you a 0.
awesome.
Yeah. So that's, yeah, thanks for bringing that up. Mm-hmm.
That looks good to me for your
Okay.
help on
So then here we have this required character counts. We've got that. Now we go to the next step where we do a find universal strings. And the find universal strings, this is the results we want to return. So these are strings in A that meet these required, this particular requirement. So let's see how we do this. So again, we are again relying heavily on our counter class. So first step, we have to iterate over the strings in A. So now let me bring the strings in A here. Or I'll just copy this for our benefit here. Okay. Okay. So we're going to go for A in A. We're going to iterate over each of these strings. So similar, it's quite similar to what we did earlier. We have to convert each of these strings into a counter. So I'm going to call this A counter is equal to counter of A. Okay, we got that. Then basically we got to say in order for this particular string to be a universal string, it has to meet all these requirements. So what that's going to mean is so we are actually iterating over this particular, the required character counts, right? So for letter in required character counts. So for example, you're looking at E, okay? And well, here's Amazon here, okay? For letter in required character counts, we're gonna say, if A counter, okay, for this particular letter, okay, so what should, the condition will be something like, if it's not meeting the requirement that you need to have at least 2 of E, then it's a problem. So if the count that we have is less than, this is required character counts at this letter. So basically you're just, you know, so Amazon, this will actually be 0 here for this letter E, okay? And so in that case, what we do is, we don't want to proceed further here because this letter is going to be universal. So we just break out of this loop. Else, you can say else, or basically, if this entire, if we have been able to iterate over this successfully without having to break, that means this word is universal. So we can just say results.append. And what I'm going to do is I'm going to append this A. So that is basically it. And then I would return my results. So this is the main, this actually will check if these counts are being met. So in this case, if I were to modify this, I'm going to bring it down back to CEO. And let's say you had OC, then you have E has to be at least 1, O has to be at least 1, C has to be at least 1. And here, then we would go like this with Amazon. Oh, then this would get eliminated. Apple doesn't need it. And then you would have your Facebook, ECO, ECO, and LateCode. And that would give you back. Oh, I got this twice. Get rid of it. And that's, I know this is spanning multiple pages here, but this is the solution I came up with. I'm going to get rid of these examples here. Required character count. Let me see if there are any typos here. Let's work our way from the bottom. First pre-compute for B, find A in that, and you have a counter for each element in B. I'm converting it into a counter, then iterating over these letters, and in the separate required character counts, just keeping track of the maximum count, returning it, and then iterating over these strings in A and seeing if the condition is being met. That it at least if it's not met, then it's not universal. But if all the conditions are met, then this is it.
Okay, this looks good. I'm looking at the logic in the inner for loop here with the break statement, made by universal strings. And I just want to make sure, maybe this is something I don't know again about Python, but that if we break on a word that's not universal, breaks us out of the inner for loop.
Yes.
So then we fall through to the else.
Oh, this actually would correspond to this one.
Okay, so yeah, I guess I'm confused about the else statement. Where is it on its own, or is it with this opening if 2 lines above?
Oh, this is actually with this one. Yeah, okay. Yeah. So this would actually break out from this, and it would actually continue on to the next A in A.
Okay.
That's what it would do.
So you break the outer loop or the inner loop.
Inner loop.
So are you also, and then continue in the outer loop? Is that correct?
Yeah, this one's going to actually continue because we have to still go over the additional strings in A. So it's like the examples here. Let's break it down.
I think I understand. It might be just language specific. I think it depends. Or perhaps it's usual that the break only works on the most immediate closest loop. And then if then execution falls through, I've never seen an else like this. I think that's where I'm getting tripped up.
Yeah. Right. The reason why it's here is because, let's say we were to take the else out and you were to break out of this loop, then you would have a bug. Basically, it would actually append this to your results.
Yes, I see that.
Yeah. So this is just to protect from that happening. So this is something very, yeah.
Okay, so it's a Pythonic thing, which is awesome.
Mm-hmm.
And it seems like the intention is to only execute the else block
Mm-hmm.
in the case that we successfully complete the for without breaking.
Mm-hmm.
Okay, that looks good. Let's see, we've got 4 minutes left in our interview.
Oh. Oh, time flew. The time complexity and space complexity. So as far as space complexity goes, initially, yeah, I was going to revisit that. I said, oh, it's going to be just O1, but we have to remember that we are also accumulating these results. So, in the case where every string in A is a universal string, then it would be O of A, basically. It would depend on that. It's going to vary, uh, depending on the number of strings in that are universal. So that's something I thought I would mention.
Yeah, I think your
Yeah.
original thought about being constant time also makes sense, at least within what is needed to solve the problem. We could just as well just return any word A that's universal here to whatever output function needs it.
Mm-hmm.
Yeah,
Yeah.
great job, Daniela.
Yes.
You got the job of being WWCode for us all.
Oh, thank you. All right. So I know we have a few minutes, and let's see. Did anyone have questions? I don't know if we can, Elaine, if you want to spend a minute or two, or Michelle, if you want to take over, that's fine as well.
All right. Well, first off, thanks to Women Who Code for having me here today. I run a company called Interviewing.io. I was a software engineer for about 5 years. Then I worked as a recruiter, and then I started this company in large part because I was frustrated with technical hiring. And I think one of the most frustrating things about technical hiring is technical interviews. And it took me a while after having messed up a lot of them to realize that it's kind of a game, and you just have to internalize that and practice and drill, and then you get better. So what Interviewing.io does is exactly that. We have a platform where anybody can practice technical interviewing completely anonymously with a senior software engineer from a top company like Google or Facebook or Dropbox. Basically, you just get paired up with these interviewers, and they run you through a really realistic mock interview and give you actionable feedback at the end and tell you where you're at and how to get better. We used to be free. We're not free anymore, sadly, in the wake of COVID, but we do have a raffle that we're running with WWC, where if you sign up with the link that I hope WWC will share, thank you, then one person is going to win a completely free professional interview. That'll be, again, with an interviewer from a company like Google or Facebook. And then one lucky person will win a $30 credit. The last thing I'll say is, we know not everybody can pay. So we recently launched this really cool thing where you can defer payment until you get a job. So you can practice on us and then only ever pay us once you're in a better position. So I hope you'll try it out. Technical interviewing sucks, but it gets easier. And the best way is to join groups like this and practice as much as you can. Thanks again for having me. And if anyone has any questions, love to answer them now, or you can always email me I'll put my email as well. If there's ever anything we can do to help, Elaine at interviewing.io. That's all I got.